Have you ever stopped to think about how our planet, this massive solid ball of rock, actually breaks? It seems kind of impossible, right? But the Earth is constantly cracking under incredible pressure. Today, we're going to unpack the simple but super powerful mechanics behind one of geology's most basic ideas, the fault.
All right, to get started, I want you to just picture something simple. Go on, imagine you're holding a chocolate bar. You can feel it, right? It's solid, it's rigid. Now, you bend it, just a little bit, and for a second, nothing really happens.
But what happens when you add a little more force? You push just a bit harder and snap, it breaks. That clean, sudden break, that's exactly what we're talking about today. Just, on a planetary scale. You've basically just created a tiny little fault.
So here it is, the official definition. A fault is not just any old crack. It's a fracture in the Earth's crust where, and this is the most important part, the rocks on either side have actually moved. They've shifted, just like the two halves of your chocolate bar slid a little when it broke. And this brings up a really important point. A simple crack in a rock, where nothing has shifted. Geologists just call that a joint. But the second you get movement along that crack, boom, it becomes a fault. So the one thing to remember is this. A fault isn't just a crack. It's a crack that moved. That's the whole game.
So, that leads to the next big question. What's causing all this movement anyway? Why do these faults even happen? The answer, in one word, is stress. The Earth's crust is not just sitting there. Nope, it's being constantly pushed, pulled, and twisted by some absolutely incredible forces.
First up, you've got compression. This is a squeezing force. It's literally pushing rocks together like they're in a giant vise. Just imagine two tectonic plates crashing into each other. That is compression on an unbelievable scale. Then we've got the total opposite, tension. This is a pulling apart force. It's a stretching force that tries to rip the crust apart. Think of a giant rift valley where the land is literally being stretched out until it breaks.
And finally, there's shear stress. This is what happens when forces slide past each other, moving in opposite directions. It's not a head-on crash or a direct pull apart. It's more of a powerful, grinding sideswipe motion. So how do rocks actually handle all this stress? While deep down inside the Earth, where it's super hot, rocks can actually bend and fold almost like silly putty. But up here, near the surface where it's cooler and the rock is more brittle, they can only take so much pressure before they hit their breaking point. They snap. And that snap, that sudden break with movement, that's a fault.
So it makes perfect sense, right? These three types of stress, squeezing, pulling, and sliding, each one creates its own special kind of fault. There are basically three main ways for the Earth's crust to break, and it all depends on which of these forces is at play. Let's start with the one caused by tension, or pulling apart. It's called a normal fault. The best way to picture it is to imagine stretching a thick rubber band. As you pull it, it gets thinner in the middle, and then it just tears, right? And one piece usually drops down a little. That's pretty much exactly what happens with a normal fault. It's caused by that tensional stress pulling the crust apart. Now, geologists have names for the two chunks of rock. The easiest way to remember it is to imagine an old miner standing in a tunnel that goes right through the fault. The block of rock above their head is the hanging wall, and the rock under their feet is the footwall. In a normal fault, the hanging wall slides down, stretching the crust and creating things like massive rift valleys.
Okay, now let's flip to the opposite force, compression, or squeezing. For this one, called a reverse fault, just imagine squeezing a really thick book from both ends. What happens? The pages buckle up and slide over each other to deal with the pressure. And that's a reverse fault in a nutshell. It's caused by compression, squeezing the crust together, and this time the hanging wall gets pushed up and over the footwall. This whole process actually shortens the crust, and it's the main engine that builds mountains. Seriously, the amazing Himalayas? That's what happens when this kind of faulting goes wild on a continental scale. Finally, we've got our third type, the one caused by shear stress. And for this one, you can do the analogy yourself right now. Just put your hands together, flat, palm to palm, and slide one hand forward and one hand back. That horizontal movement, that is the heart and soul of a strike-slip fault. With a strike-slip fault, the blocks of rock are moving sideways, horizontally past each other. There's almost no up and down motion at all. And the most famous example of this on the entire planet is the San Andreas Fault out in California. That's where the Pacific Plate is just grinding its way north past the North American plate. Okay, so we have these enormous blocks of rock moving all over the place. But why does that movement lead to something as violent as an earthquake?
The key thing to understand is that the movement is not smooth. It is not gradual. It's all about that sudden snap.
So the whole process happens in about 3 stages. First, the two sides of a fault get locked together. Friction holds them stuck. Second, as the tectonic plates keep on moving, a huge amount of strained energy builds up in the rocks. It's like coiling a giant spring tighter and tighter. And finally, when the stress just gets to be too much for the friction to handle, the fault suddenly slips and all that stored energy is released in one violent, explosive moment.
Probably the best way to feel this in your head is to imagine bending a plastic ruler. You can bend it more and more and more, and all that energy is being stored silently inside the plastic. But then you hit the limit, and it doesn't just gently unbend itself, it snaps. That sudden release of energy is the earthquake. The shaking, the seismic waves, that's all from the energy of that snap.
So we've looked at the stresses, we've looked at the different ways things can break, and we've looked at that violent release of energy. So what's the big idea here? What is the single most important thing to take away from all this?
It's this. Faults are not just some random act of destruction. They are a necessary part of how our planet works. You should think of them as the planet's release valves. They're Earth's natural and totally inevitable way of letting go of the enormous stress that builds up from the constant motion of its tectonic plates.
And this table really brings it all home. You can see the relationship so clearly. The type of stress directly tells you what kind of fault you're going to get and which way the rocks are going to move. Tension pulls things apart, the rock drops down. Compression squeezes them, the rock gets pushed up. Shear grinds them, they move sideways. Stress, fault, motion. It's a perfectly connected system.
So we'll end on this thought. We know that these faults are the release valves for stress that builds up slowly, silently, sometimes for hundreds of years. So the question to leave you with is this. As you look at our dynamic planet, where is that stress building right now, just waiting for its next sudden release?